So today we will discuss chapter 5, effective stresses, capillarity and permeability, engineering service examination, previous year question. Okay. So today we will discuss this chapter. Very important for engineering service examination. It is very important chapter. So let me complete this chapter. Okay. One by one. So the first question is about quicksand condition. Okay. So uniform, let me change the color of pen. A uniform sand stratum 2.5 meter thick and a specific gravity of 2.62 and a natural wide ratio of 0.62. So the thickness of stratum is H is equal to 2.5 meter, 2.5 meter. A specific gravity G is equal to 2.62 and the natural wide ratio E is equal to 0.62. The hydraulic head required to cause quicksand condition in the sand stratum is. So for quicksand condition, the critical hydraulic gradient IC is equal to G minus 1 divided by 1 plus E. Okay, IC is nothing but IC is equal to gamma submerged by gamma W. Okay, and when you put this gamma submerged, what is gamma submerged? Gamma submerged is equal to gamma sat minus gamma W. And gamma sat is G plus SE. S is 1. SE divided by 1 plus E into gamma W minus gamma W. So in submerged case, saturated case, S is equal to 1. Okay. So this will become, when you solve this, gamma submerged becomes, this is equal to G plus E divided by 1 plus E minus gamma W. If you take gamma W outside, if you take gamma W outside, let me erase first. Let me this part separately, uh, here separately. Yeah, this is separately here. Okay. So gamma submerged is equal to gamma saturated minus gamma W, and gamma saturated G plus SE divided by 1 plus E. In saturated case, S is equal to 1 into gamma W minus gamma W. Take gamma W common out. So G plus 1 divided by 1 plus G plus E divided by 1 plus minus 1 into gamma W. If we take gamma W as common, so this is 1 plus E, G plus E minus 1 minus E to gamma W. So E get cancelled out, and this is G minus 1 divided by 1 plus E into gamma W. Therefore, ICR is equal to gamma submerged by gamma W, and gamma submerged is G minus 1 divided by 1 plus E into gamma W by gamma W cancelled out. So this is G minus 1 divided by 1 plus E. Okay. So when you use this formula, G minus 1, G is what? 2.62 minus 1 divided by 1 plus E is 0.62. So this is 1.62 divided by 1.62. This is 1. So IC is equal to 1. And IC in this case is what? The head, that is called head causing the flow divided by length of flow, L. Okay. So from here L is equal to, this implies that it is asking about the hydraulic head required to quicksand condition. So this is hydraulic head required. This is 1 into, this is capital H actually, length of flow capital H here. This is capital H. So this is capital H. This is equal to 1 into 2.5. This is equal to 2.5 meter. So this will be the answer, 2.5 meter. Very simple. Just remember this formula. Just remember this formula. Okay. Just remember this formula and this formula also. I is equal to head causing flow divided by length of flow. Okay. To hydraulic gradient. It's very important. Okay. Let us understand about the quicksand condition. What is quicksand condition? Okay. So if we discuss this in detail, then let us discuss what is quicksand condition first. So what is quicksand condition? Quicksand, quicksand, quicksand condition, quicksand condition. So in case of upward seepage, in case of upward, in case of upward seepage flow, in case of upward seepage flow, if the upward seepage force, if the upward seepage force, if the upward seepage force becomes equal to the, becomes becomes equal to the, becomes equal to the buoyant weight, becomes equal to the buoyant weight, becomes equal to the of buoyant weight of soil, the effective stress in the soil, the effective stress, the effective stress in the soil, effective stress in the soil becomes zero, becomes zero. And in another word, in other word, in other word, in other word, in other words, uh, by increasing the head difference, by increasing the head, by increasing the head difference h, head difference h, that is uh, this head is causing the flow h. If it is increased, it is possible, it is it is possible to reach a condition, to reach condition, is possible to reach a condition where the effective stress, where where the where the effective stress, where the effective stress in the soil becomes zero, in the soil becomes zero. Okay. So in case of downward flow condition, some note point, in case of downward flow, in case of downward flow condition compared to no flow condition, compared to no flow condition, effective stresses increases by effective stresses increases by effective stresses increases by I Z gamma W. Z is the depth, I is the hydraulic gradient, and gamma W unit weight of water. So effective stress is increased by this much amount. But in case of downward flow, in case of in case of upward flow, in case of upward flow, upward flow, in case of upward flow, condition compared to condition compared to condition compared to no flow condition compared to no flow compared to no flow condition, effective stress decreased by effective stress decreased by this is by the same amount I Z gamma W. Okay, that is in case of upward flow, and this is the case of downward flow. Okay, so this causes the quicksand condition. So for quicksand condition, for quicksand quicksand condition, that is sigma, the effective stress becomes 0, and effective stress in this case in upward flow is decreased by this much amount compared to no flow condition. So in no flow condition, effective stress is total stress, effective stress is total stress minus pore water pressure, and this effective stress is decreased by, that is, I critical Z into gamma W, and this will be 0. So sigma is Z into gamma sat minus U is Z into gamma W minus IC Z into gamma W equal to 0. And gamma sat, you know that Z and gamma sat is gamma submerged minus gamma W, okay, minus Z gamma W uh, minus Z gamma W minus Z gamma W minus IC to Z gamma W. So from here, uh, this is decreased by this much amount, and this is gamma W Z is ICR is so I'm writing this step is last step is wrong. This is not correct. Actually this step gamma sat is not gamma submerged gamma W. Okay, so actually this step is wrong. I am erasing this part. I am erasing this one. Not able to erase. Why? Okay, so this part is wrong. Why it is wrong? So gamma sat is equal to gamma submerged minus gamma double. This is wrong. Actually, gamma submerged is equal to gamma sat minus gamma double. Okay, so this is plus, not minus. Okay, so remove this. So I'm further taking after this step. So if you take z common from this and this is gamma sat minus gamma w minus ICZ. Gamma w is equal to 0, and gamma sat minus gamma w is gamma submerged. So z into gamma submerged minus IC critical hydraulic gradient z into gamma w is equal to 0. So from here IC is equal to what? IC is equal to z gets cancelled out. So that is gamma submerged by gamma w. And when you calculate this, you will find G minus 1 divided by 1 plus E. So this is very important formula, and this will come under condition when effective stress becomes 0 in this case and soil looks like boiling. Okay, and this is called quicksand condition. Okay, so and uh, IC is what? IC is, and in this case the final formula is mm, I is equal to gamma submerged by gamma w, and this is G minus 1 divided by 1 plus E, and I is equal to head causing the flow divided by length of flow. That is, if I'm taking it capital H, then the length of flow. So here H is, what is H? Head loss occurs during seepage. Head loss occurs during seepage, and capital H is length of flow. Length of flow. Capital H is length of flow. This is quicksand condition. So to obtain quicksand condition, quicksand to obtain quicksand condition, downward effective weight has to be downward effective weight has to be balanced by seepage pressure seepage pressure seepage pressure upward seepage pressure, that is that is uh, I gamma w into z. Okay, for finding of critical hydraulic gradient ICR, that is H gamma submerged, downward effective weight, that is H gamma submerged downward effective weight, must be balanced by IC H into gamma W. So from here also you get IC is equal to gamma submerged by gamma W, and when you solve this you will get this expression G minus 1 divided by 1 plus E. Okay, this is very important formula. And the condition is also important. The condition is also important. Okay, these are same condition actually. this condition, this statement, and this statement all are very similar statements. Okay. So next point is for usual range of wide ratio, for usual range of wide for usual range of wide ratio, that is E is from 0.6 to 0.7 in in sand and with a specific gravity and with a specific gravity of GS is equal to 2.65. ICR will approximately equal to 1. Okay, when you put these all values in this formula, you will get ICR approximately equal to 1. Okay, next point is at critical hydraulic gradient, at critical hydraulic at critical hydraulic gradient quicksand condition occurs. Quicksand quicksand condition occurs in in sand but not in clay, but not in clay but not in clay because in clay cohesion exists. cohesion exists Cohesion exists. Okay, thus thus even if effective stress becomes zero, that is tau in this case is equal to cohesion plus sigma tan phi. Even if sigma prime becomes 0, this is not equal to 0. Okay, next point is in practice in practice quicksand condition occurs. Quicksand quicksand condition occurs when excavation is when excavation is being made below water table below water table water table, and water is being pumped out and water is being pumped out from excavation from excavation pit to keep area free from water, to keep area free from water free from water. Next point is quicksand condition can be prevented by quicksand condition can be prevented by quicksand condition can be prevented by lowering of water table lowering of water water table, lowering of water table at at site before at site before at site before excavation before excavation, or by increasing the or by increasing the increasing the upward flow upward flow or by increasing the length upward flow length by providing a seat pile wall by providing a, by providing a seat by providing a seat pile wall by providing a seat pile wall. Another method adopted another method another method adopted another method adopted at site to avoid at site to avoid quicksand condition quicksand quicksand condition is adding of surcharge is adding of surcharge adding of surcharge that is additional weight that is additional weight on the excavation side on the excavation side to increase to increase the net weight of the soil mass to increase the net weight of soil mass. Okay. Next point is quicksand condition generally does not occur. Quicksand condition quicksand condition generally does not occurs in coarse sand in coarse sand coarse sand because in equation because in equation Q is equal to KIA for I to be more for I to be more Q has to much more Q has to much more Q has to much more because K is large because K is large because K is large for coarse sand for coarse sand. This large seepage this large seepage discharge Q is generally not available not available in the field condition in the field condition. Okay, so This is all about quicksand condition. Hope you understand quicksand condition and the question related to this. If numerical is asked related to quicksand condition, then you must remember this formula. IC is equal to G minus 1 divided by 1 plus E, and IC is also equal to gamma submerged by gamma W, and IC is also equal to CPS head divided by length of flow divided by length of flow, capital H. So this is all about quicksand condition. Okay. Now we will discuss question number 2. So question number 2 is, if during a permeability test on a soil sample with a uh, falling head permeameter, equal time intervals are noted for drop of head from H1 to H2 and again from H2 to H3, then which of the following relation would hold good? Okay. So this question is about falling head test. There are two tests. One is falling head test to know about permeability of soil. That is done for um, getting permeability of soil. There are two tests. First one is constant head permeability test, and second is falling head permeability test. And the equipment is called permeameter. So uh, in this question, it is talking about falling head, that is variable head or falling head permeability test. Okay, it's falling head permeameter. So in this case, uh, you know the formula for this. K for in case of variable head or falling in case of falling head uh, permeability test, permeability test in case of falling head permeability test, mm, K permeability K is equal to L sample length into A area of standpipe divided by time into area of soil sample Ln H1 by H2. Okay, in this case, mm, this is standpipe, yeah, and yeah, here we maintain the constant head. Okay, constant head chamber. This is constant head chamber, constant head, constant head chamber, and this is standpipe, standpipe area is equal to small a, and this is soil sample. Says soil sample, this soil sample, soil sample, soil, soil sample, and area is A of this soil sample. Okay. Now, water is filled in this. This is water. Soil sample also water will be there. Okay, this is water. And it is time taken to fall this height is time t. This area is A, capital A discussed, small a discussed. L is this one, length of the sample. This is L. Okay, and the time taken, this is time which is taken to fall this water. And this is suppose H2, and before some time t, this will be H1, and after time t, that is time is equal to t, time is equal to t1, and this is at time is equal to t2. This at time is equal to t2. So t2 minus t1 is equal to t. Okay, so here this is t, h1 to h2. This is permeability K. Okay, so K is equal to L small a divided by T into capital A ln H1 by uh, from head H1 to H2, so H1 by H2. The soil sample is same, therefore again the permeability will be same, that is K, and this is L into A. Length of sample is same, time is same, area is same, and this is ln. This time this is falling from H2 to H3, so H2 by H3. This is equation 1, this is equation 2. So from 1 and 2, ln H1 by H2 is equal to ln H2 by H3. So from here H1 by H2 must be equal to H2 by H3. So H2 square is equal to H1 into H3. So from here H2 is equal to square root of H1 into H3. H1 into H3. Okay. And this is H2 is nothing but GM, geometric mean of H1 and H3. Geometric mean of H1 and H3. Okay. How this formula comes? If you want to derive this formula, so let me derive this formula. So according to this, answer will be B. So derivation of this formula, derivation of K is equal to LA TA ln H1 by H2, or this is also K is equal to, this is also equal to this is also equal to, this is also equal to 2.303 LA by TA log, in this case the base is 10 H1 by H2. Okay, so I'm drawing the figure again. I'm drawing the figures again. So This is 10 pi. This is 10 pi. And put the sample in this chamber. And then we will maintain constant head. This is constant head chamber. Okay. This is soil sample. Length is L, area is capital A, and standpipe cross section area is equal to a small a. Okay, small a. So at t is equal to 0, suppose at t is equal to 0, water level at this position, this is at time is equal to 0, and the head which is causing the flow at this point, let me take it as h1, and at time t2 and at time is equal to t, the head causing flow is h2. Okay, so delta t is equal to the time taken is t. So now take at any time uh, t, let me take this as t is equal to time is equal to for this uh, t prime. Okay, so at any time t, uh, or let it t, so anytime t, suppose the water is at this position and head is at this point, head is h. This is at time t, this is at time is equal to t, and in time dt it falls by dh. This fall is dh at time t is equal to t plus dt. This is the fall. So if discharge from soil is q, so q into a, so using continuity equation, using continuity equation or conservation of mass or conservation of mass, both are same thing. Okay, using continuity equation or conservation of mass, water which is water falls in time dt will pass through the soil, and if discharge is q, so q into area is volume passed through this soil sample in time dt will be equal to uh, dh into a, dh into a. This is the minus sign because h is going down, falling, h is decreasing. So this is positive quantity and dh will be negative quantity, so you have to make it positive by multiplying with extra minus sign. Okay, and you know that q is equal to k into I. Q, actually this is not q into a, this is q into t. I'm very sorry. This is q into t. in time dt na, so q into dt. So in time dt, the discharge passed through this sample will be q into dt, and that must be equal to minus a into dh, that is fall of the water level, the volume of water which is fall down in time dt. Okay, so this is ki into a is q, and dt is equal to minus a dh. Okay, and you know I is equal to head causing flow divided by length of flow is L into A into dt is equal to minus A into dH. So from here, if you take this H right side, then Ka by L dt, Ka by L dt is equal to minus A dH by H. Okay. Now integrate both sides. This is from at t is equal to 0, that is H1, and as t is equal to t, time is equal to t prime, that is H2. Okay. Here t prime is the time taken to fall the water level from H1 to H2, that is t prime here. Okay. So this is Ka by L into T is equal to minus A ln H2 by H1. So from here, Ka by L into T is equal to A ln H1 by H2. Therefore, T is equal to La by At ln H1 by H2, or this is 2.303 La by At log base 10 H1 by H2. So this is the formula uh, proved here. Okay. So this is the formula proved here. Okay. So so let me write down some points. Sometimes the permeability test is conducted using the consolidometer. Sometimes the permeability test, the permeability test is conducted is conducted using the consolidometer. Consolidometer instead of the instead of the instead of the permeameter. Permeameter. Permeameter mold. This is permeameter mold. Okay? Permeameter mold. The fixed ring consolidometer is used. The fixed ring consolidometer is used. Fixed ring consolidometer is used as a variable head, as a variable head per millimeter millimeter by attaching a standpipe to the base, by attaching a stand pipe to the base, to the base. Okay. So this is all about question number 2. Now question number 3. If a saturated density of a given soil is 2.1 ton per meter cube, so gamma sat is equal to 2.1 ton per meter cube. The total stress T and the effective stress E of saturated soil stratum at a depth 4 meter, at a depth 4 meter, at a depth 4 meter, T total stress T, what is total stress T, and the effective stress E will be what? So total stress T is gamma sat into H. This is 2.1 into 4, 8.4 ton per meter square. And effective stress E is equal to T minus 4 water pressure, total stress minus 4 water pressure. That is T is 8.4 minus 4 water pressure is uh, gamma W into H. So in ton per meter cube, gamma W is 1 ton per meter cube. This is 9.81 kilonewton per meter cube. That is 1. We can take it 1. So 8.4 minus 1 into 4. 8.4 minus 4. This is 4.4. So 8.4 and 4.4. 8.4 and 4.4. D will be the answer. Okay. So total stress T is equal to effective stress, effective stress, effective stress E plus pore water pressure, pore water pressure U. Okay. Now question number 4. So we will discuss question number 4 in next video. So this is all for today. This is all for today. Question number 3. Thank you.